Okay. You got the list. The only thing I did not put on the list was carbocation rearrangements. But again, the rule for carbocation rearrangements is I would have to either tell you to do that in the problem or the mechanism, or I would give you a reactant and the product, and you have to write the mechanism to get to that product. And in getting to that product, it would have to involve a rearrangement. So that was the only thing that I left off the list. So what are your questions? And you can send them to me on Piazza if you don't want to ask in person. Go through and see what I've got. Let's see, what do I have? Can you show the full mechanisms for the addition reactions of H plus, H2O, and HX? I think I did that. Done. So actually, I did that. I don't, it's, all these are, I thought they were getting rid of the ability for you to submit stuff anonymously to me, but apparently we are making very good use of that. So I don't know if that came from somebody in here or not, but this is I put the mechanisms of adding H plus H2O online in the Piazza. I gave examples of those. I can come up with other alkenes for new problems. That's not a big deal. But they all kind of look the same. Do you have any new questions? Otherwise, I'm just going to kind of, yes.
When it's a reaction that doesn't add an H plus, that adds in two different things, I have trouble figuring out if it's my carbon which one's going to add the lesser substituted carbon.
Let's unpack that. So whenever we have a double bond, Markovnikov means that we're going to add the E plus, we're going to add an E plus and a nucleophile. And the E plus then is always going to go to the carbon that has the most hydrogen, simply because then the carbocation ends up on the most substituted carbon, and that's always going to make the carbocation that's the most stable. So in terms of our reactions, we have things where we add H plus explicitly. H plus and a halogen, H plus and water, H plus, and again, there's really very little difference between HOH and ROH. So H plus water is going to also lead to H plus alcohol. So for those reactions with H plus, those are the three, I think, from the table that I gave you. The other thing we can do is we can add a Br plus, which is what we're doing when we add Br2. So we add Br plus, and then we essentially add a Br minus. Now in that case, it doesn't matter because there's two Brs. So if I said, let's take this alkene and let's add Br2 to it, first of all, I'm going to end up with a bromonium ion. But really, when the Br minus comes in and adds, which carbon is it going to add to?
One on the right.
Okay, I got one on the right, one on the left. Should have stayed on the left. In the bromonium ion, where is the nucleophile going to add? It's going to add to the carbon with the greatest delta positive charge. So it's going to add to the carbon that has the greatest delta positive charge. Which carbon is that? The one that is most substituted. So the Br minus is going to come in and it will add to the left carbon. And then the pair of electrons will go this way, so that in the end what I will end up doing is adding the Br, and then I will have the Br there. Now the problem with this reaction is, in the end, I don't know which Br added first and which Br added second. But this Br should add to the carbon that has the most delta positive charge. If I now change that problem and I say, let's add Br2 and H2O, what's going to happen? I'm going to add my Br plus to again make a bromonium ion. But now it's the water that's going to come in and add. And so which carbon is the water going to add to? The one on the left, because it's the carbon with the most delta positive charge. It's the carbon that's most substituted. So the water will come in and add to the carbon on the left, and I will end up forming an oxonium ion. Remember, you don't want to skip those steps. You'll end up with the oxonium ion, and then the oxonium ion is going to lose H plus to give you the OH. So with Br plus and Br plus with the adding H2O, which is going to end up adding OH, that's also an electrophile, which is going to replace the H plus. So we called Br2 H2O2 addition Markovnikov because the Br ends up on the carbon with the most hydrogens. The OH ends up on the carbon that's most substituted. So Br plus is replacing H plus in that mechanism. And then the only other electrophile that we were adding was, remember that we were adding the mercury acetate and water. And so the mercury acetate was basically creating a triangle, and we were adding mercury plus. So the water would then end to the carbon that's most substituted at the end as well. So for all of these electrophiles, we're always adding the electrophile to the carbon with the most hydrogens and then adding the nucleophile, whatever that is, to the most substituted carbon. So all of them on the chart that said Markovnikov, that's characteristic of Markovnikov. You add an electrophile, then you add the nucleophile. Now for bromine and mercury, they bridge so that you form the triangle, which means not only are they adding Markovnikov, they're also adding 100% trans.
For the first one, 50-50 though,
Right.
why is that again?
The reason that the first three are 50-50 is because the H plus isn't big enough to bridge. And so it has to make a choice. And so it's going to make its choice to add to 100% to the carbon with the most hydrogens. That's going to leave the other carbon as a pure carbocation. So then the nucleophile is going to add 50% from the top, 50% from the bottom. But when the nucleophile, or when the electrophile is big enough, like bromine and mercury, it bridges, and that causes 100% trans. So hydrogen isn't big enough to bridge. It's got to make a choice.
Why do we put in the delta positives if it's not a transition state?
Because overall, the bromonium ion has a +1 charge. So we have to show somehow where that +1 charge is. And so by putting the two delta positives in, that's where those two add up to +1. So it's an intermediate, but it has a +1 charge overall. So that's why we have to put those delta positives in. What else? All right, then let me ask you this question. What would the major product of this reaction be? Oh no, are we stuck? Anybody have an answer? Anybody stuck? You're stuck? You need help? Somebody give her some help. I've been doing this on the exam. Oh, God, I can't remember. I can't remember what. Okay. Go back to basics. Oxygen species plus what? H plus Cl minus. If I had to write the mechanism of this reaction, what would it be? What's the first step? Tommy? Get rid of the D part. Protonate the oxygen. Whenever we have an oxygen species and we're adding an acid to it, protonate the oxygen. Okay? So I'm going to protonate the oxygen. That oxygen species happy with the positive charge? Not really. So what is it going to do? No. I mean, sort of it's going to leave, but it's going to leave being bonded to one of the two carbons. But that oxygen with its positive charge is going to do what? It's going to shove the positive charge down to the carbons. So it's going to form something that looks like this. Actually, we can take away this, if I can. We can take away the partial bonds, and we can say, well, it's going to put the positive charge, it's going to put a good chunk of positive charge down on the carbons. Now my Cl minus is going to come in. Which carbon is it going to attack? The most substituted, because that carbon has the most delta positive charge. Right, what I wanted to do here was I wanted to take out those and write it kind of like this. Why did I want to do that? Isn't that what I did over here? So when we're opening up epoxides, I should just get right to the point. When we're opening up epoxides, we're basically using the same principles that we use for bromonium ions and for the mercury ions. So when we protonate the oxygen, we're making a species with a positive charge. That's going to push all the electron density down to the carbon. To the two carbons, the chlorine is going to come in and add to the carbon with the most positive charge, and then the OH group is going to swing over to the other carbon, so that the final product that we make is going to have the OH and the Cl are now going to be 100% trans, but the nucleophile will add to the carbon with the most hydrogen, or with the most substituents. So what I'm trying to show here is it's the same principle. And epoxide ring open, acid catalyzed, I guess as they call it. It's not quite catalyzed, but acid catalyzed ring opening also has the same principles as the bromonium and the mercurium ions. So if you don't remember that, you need to. I'm open for questions. Somebody did ask, can we go over a reaction with tertiary butoxide? Sure. Now, if you look at some of the older exams, I usually like to take this kind of molecule with the cyclohexyl halides, and I like to pair them up with what would the reaction be with NH2 minus, what would the reaction be with tertiary butoxide, what would the reaction be E1, what would the major products be. I think in last year's exam I also threw in what would the reaction be if we used a strong or a weak nucleophile, because people asked me about a couple questions from last year's exam that I put, I broke down the answers and put those online or on Piazza last night. And if you're not like looking at Piazza, you're missing a lot of stuff that I guess I'm assuming that everybody's looking at, but I could be wrong. I'd have to look at my statistics to see how many people are looking at it. It's probably not 100%. But if it's not, and you're not the one of the 100%, then you might want to peruse it, because there's a lot of good stuff on there. But how am I going to solve this problem? What's my approach going to be? Well, my first question is, what mechanism is it? E2. How did you know that it was E2? It's tertiary butoxide. It's a strong base, which is tertiary butoxide, but any tertiary butoxide, any NH2 minus, those are automatically E2. So the minute you see tertiary butoxide or NH2 minus, E2. Okay, so for E2, now I know it's an E2 mechanism. What should I do next? I would identify the alpha and the beta carbons, and also then that'll lead me to identifying the alpha or the beta hydrogens. So I have 3 beta carbons, which means I have 3 beta hydrogens. The CH3 has 3 beta hydrogens on it. So if I wanted to, I could write that as a CH2 with an H. So there's my 3 beta hydrogens. So that's the first step. Now, because this is E2, only the beta hydrogens that are anti-periplanar can be removed. What does that mean for the ring? That means the beta hydrogens have to be, sure, they have to be attached. Oh. Well, what does dashed mean in this case? Trans. They have to be trans. I don't want somebody to think they always have to be dashed, because if I flip the chlorine in the methyl group, then they're not going to get that problem right. So they got to be trans. So can this hydrogen be removed? No. Can this hydrogen be removed? Could be. How about the CH2H? The hydrogens outside the ring, the beta hydrogens outside the ring, can always be removed, because they have free rotation to rotate around and become anti-periplanar to any leaving group. So the hydrogens outside the ring can always be removed. The hydrogens that are attached to the ring must be trans to the leaving group. So now I have 2 possible products here, right? So step 3 would be, let me write my products for the removal or deprotonation of those two beta hydrogens. So those are the two possible products that can be formed. I cannot form a double bond upwards to the carbon with the CH3 on it. So those are my two possible products. And those are my two possible products for either tertiary butoxide or NH2 minus. Okay? So in terms of steps here, first thing is tertiary butoxide tells me E2. Identify the alpha and the beta carbons and then the beta hydrogens. Which beta hydrogens are anti-periplanar or trans to the leaving group? Identify which ones those are, because then the fourth step is write the possible products, or identify the possible products, at least in your head. The final step is which one's going to be major. So I have to look at the base. It's tertiary butoxide. The major product is going to come from tertiary butoxide removing the beta hydrogen that is least sterically hindered. So now I'm going to choose my major product. It's going to come from the carbon that was least sterically hindered. Which one is that? So what's the major product, A or B?
A.
We all agree it's A? Do we all know why it's A? I know it's least sterically hindered, because that's what would follow. But why is it the least sterically hindered? Because what type of hydrogen is this one? Primary, secondary, or tertiary? This one is a primary hydrogen. And down here, what kind of hydrogen is this one? It's tertiary. So when we're looking at this, the least sterically hindered hydrogen is the first criteria that we want to use is primary, secondary, tertiary. With primary being less sterically hindered than secondary than tertiary. If we had two primaries or we had two tertiaries, we might want to look at the groups that surround that hydrogen, and if there's bigger groups, then that would be less favored than if there's smaller groups. And hopefully if that makes sense, great. But somebody did ask, why do you remove the hydrogen outside the ring and not inside the ring with tertiary butoxide? It's because in general, the hydrogens that are outside the ring are going to be either primary or secondary, whereas the hydrogens that are in the ring are going to be usually tertiary, particularly if they have a stereochemistry. It's because there's another alkyl group over here that automatically makes them tertiary. So, Olivia. With a non-cyclic? Yes. So is everybody okay with this one? With this kind of problem? And there were two problems like this on last year's exam. And I asked for all those different things. So I broke them down, hopefully, into each reaction. So, a non-cyclic one. So the non-cyclic one would be something that's going to be in a sawhorse, and it would have something like, I don't know, you'd have like a Cl here, maybe we would have an ethyl group here and a hydrogen there, and maybe a methyl group here and a hydrogen there, and maybe an ethyl group over here. So if I have this kind of a molecule, I can ask you two questions about it. Well, I could ask you three. I could say what would be the major product under E1, but that's boring. So what I could ask you is, what's the major product with NH2 minus, or what's the major product with tertiary butoxide? And those may not be the same answer. Okay. So, steps. Number one, NH2 minus tertiary butoxide. What does that mean for the mechanism? They're both going to go by E2. And I'm stressing that because that's important. If the reaction was not going by E2, we wouldn't care about the stereochemistry. Because any hydrogen, any beta hydrogen can be removed because it doesn't have to be antiperiplanar. But as soon as I know it's E2, every hydrogen has to become antiperiplanar. And in this case, that's going to set up the stereochemistry for one of the two products. So next step, identify alpha, beta carbons, and identify the beta hydrogens that could be lost. So here's my alpha carbon. Here's beta carbon 1, beta carbon 2. So there's two beta carbons. That is the hydrogen in the square now is beta hydrogen. And then up here, if I wanted to, I could make this, that's a CH. There's my other beta hydrogen. So my two beta hydrogens I put in squares. So let's call this beta hydrogen A and beta hydrogen B. So let's take the easier of the two problems. Which would be which one? Tertiary butoxide or NH2 minus? How about the tertiary butoxide? So, which hydrogen is the tertiary butoxide going to go after to form the major product? What did we just say? The beta hydrogen, that is the tertiary butoxide's going after the beta hydrogen that is the least sterically hindered, which in this case is beta hydrogen B. Because beta hydrogen B is what kind of hydrogen is this? Primary, secondary, tertiary? Secondary. That's a secondary. What kind of hydrogen is beta hydrogen A? Tertiary. So tertiary butoxide is going after beta hydrogen B. In terms of writing that product then, so what we would have is we would have the tertiary butoxide coming in, grabbing this hydrogen, that pair of electrons goes down there and the chlorine gets kicked off. So in terms of writing that product, everything on the left side here, that group is unchanged. So everything on the left side of the molecule stays the same. What happens? I'm forming a double bond between that carbon and then there would be a CH and a CH3. And then down here would be the H because the chlorine got kicked off. So the double bond is going to go up to form the double bond between the alpha carbon and the beta carbon that had HB attached to it. Do I have to mess with stereochemistry there? Do I have to put the hydrogen antiperiplanar to the chlorine? Technically, yes, I do, but is it going to matter in the stereochemistry? No. It's not. Because there's no bold and dashed wedge on that hydrogen. And technically, there's two hydrogens here that could be removed, so either one of them could be removed. So for that one, I don't have to worry about aligning the beta hydrogen so it's antiperiplanar to chlorine. It's going to be removed. It's not quite the same, but is to having the beta hydrogen outside the ring. The stereochemistry doesn't matter. So that's the product with the terse butoxide. That's the major product of the reaction. What happens now with NH2 minus? NH2 minus forms the double bond that is the most substituted, which is the double bond that is the most substituted equals most most substituted double bond is the most stable. Most substituted double bond is the most stable. What does NH2 give you? It gives you the double bond that is most stable, most substituted. What does E1 give you? The double bond that is most stable, most substituted. So NH2 gives you the same most substituted product that E1 does, except the beta hydrogen that's lost in the NH2 minus reaction has to be antiperiplanar, because that's the rules. NH2 minus, E2, beta hydrogen's got to be antiperiplanar. Okay. So which hydrogen is that going to be in this case? The NH2 minus is going to remove hydrogen A and form the most substituted double bond. The problem is I now have to take this molecule and I have to do what with it? I've got to orient the beta hydrogen A so that it is antiperiplanar to the chlorine, because there are two different geometries for the double bond that's formed. Okay, so we're going so the hydrogen is in the back. So let me see if I can write this again, because I'm going to write it again. So up here we had the CH2, CH3. Here we had the chlorine. Here we had the hydrogen. Down here we had the ethyl group. Over here we had beta hydrogen A. And up here we had what? The methyl group. So now what I have to do is now I've got to align beta hydrogen A and the chlorine antiperiplanar to each other, which means I'm going to have to rotate both carbons so that in the end it looks like this, HCl. So I'm going to rotate this hydrogen up, the methyl group down, the ethyl group to the back, so that the methyl group comes down here and the ethyl group goes there. So I'm just rotating like we did with Newman projections, like we've done with the sawhorse. I'm going to put the hydrogen up in this position. Over here, what am I going to have to do? I'm going to have to rotate the chlorine down, the hydrogen up where ethyl is, and then ethyl into chlorine. So I'm going to have the hydrogen there. I'm going to have the ethyl group here, and I'm going to have the chlorine now. So we've got to rotate the molecule so that the hydrogen and the chlorine are now antiperiplanar, which means now that the NH2 minus can come in, it can grab the hydrogen, have the pair of electrons move, have the chlorine get kicked off. If it does that, then I get one stereochemistry for the alkene. And so the two groups that were bold are going to be cis. The two groups that are dashed are also going to be cis. Okay. So the methyl group was bold. It's going to be cis to the hydrogen. So those were the two groups that came from the bold wedge. The ethyl groups are both on dashed wedges, so therefore they will end up cis as well. So those two groups came from the dashed wedge. Okay. So for this molecule, for this reaction with NH2 minus, the major product is this stereochemistry with the two ethyl groups cis. It is not the product where the ethyl groups were trans. Because the other possible product can't form. Because this is the product you get when the hydrogen and the chlorine are antiperiplanar. So with the non-cyclic product, with the non-cyclic reactions, if I gave you a tertiary butoxide and an NH2 minus, you're most likely going to get two different products. The tertiary butoxide, there's probably not a stereochemistry with it for the double bond because that group has freedom to rotate and it's not going to give a particular stereochemistry. But when you're removing a tertiary hydrogen, the reason that hydrogen, that beta hydrogen is tertiary is because there's two other things attached to it. If there's a bold and dashed wedge attached to those other things, it means the stereochemistry is going to be fixed. So you're going to get one of two of the possible geometric isomers, of the structural isomers. In this case, you're going to get the E or the Z isomer as opposed to the E isomer. Because we've got to rotate that sawhorse. Let me do one out. Let me do this. Let me just formally do this one. The one with the cyclohexane ring I put on Piazza, so that one's available. But if we're going to do bromine and water, No transition states, so this is just intermediates. The first step in the mechanism is to take this pair of electrons, use it to bond one of the bromines, and then the pair of electrons goes to the other bromine. So that, in essence, is adding a Br+. When I do that, I'm going to end up with the bromonium ion, which again has to have delta positive charges on the two carbons, because overall that species is +1. So that's step one. Step two then is to take the water and have it attack one of the two delta positive carbons. The water is going to attack the carbon that has the most delta positive charge, which is the carbon that is most substituted, right? We're ending right where we started. So then the water comes in, the bromine then moves over to the other carbon. So that's going to give me the oxonium ion down here. And then in the final step, I'm going to lose an H plus as the proton gives, as the oxygen-hydrogen bond breaks, the pair of electrons going back to the oxygen, so that I end up with the OH and the Br added Markovnikov, because the bromine added to the carbon with the most hydrogens, and they would add 100% trans. And if you're asking in this case, well, why aren't you using bold and dashed wedges? Well, I am not using bold and dashed wedges because this reaction really isn't stereoselective. So if I asked you for this reaction, is it regioselective? Yes, because adding the Br and the OH in differently would end up with two structural isomeric products. Is it stereoselective? Criteria number one, is it 100% trans? Yes. Criteria number two, did I make two chiral centers? There's two methyl groups, so that's not chiral. Over here, is that carbon chiral? Yes, but I only made one chiral center. Is that stereoselective? No, because by definition, whenever I make one chiral center, unless my reagent was chiral, I'm going to get an automatic 50-50 mixture of enantiomers. So in this case, this reaction would be regio, and it would be not stereo. So it would be regioselective only. And so I gave example mechanisms for all the ones that I had on the sheet in Piazza yesterday. There were a lot of questions from yesterday. There's a lot of questions from today. So that would be, you can check those out as well. Right. If you have questions, either come see me, email, or put them on Piazza and I will answer them. I will be in this weekend. I can guarantee I'll be in the afternoons. I'll leave the door open so that you, doesn't do me any good to be here, but lock the door, so, well, it does, but, so if you have any questions,